Suppose Alice and Bob generated this Bell state here while they were together long ago. And when Bob left, he took the second qubit of the Bell state with him. So this green qubit here. And now Alice needs to send Bob a new qubit, ket psi. And she doesn't know the state of ket psi. That is, she doesn't know the amplitudes alpha and beta that make up alpha ket 0 plus beta ket 1. And she can only send Bob classical information. Well, she can do this using quantum teleportation. And so that's going to allow her to take advantage of this entangled Bell state here and send ket psi to Bob with minimal classical information. So this is the actual circuit that we're going to be analyzing here. In blue, I've labeled the different gates involved. And so this top wire, these two top wires, belong to Alice, and this third wire, third qubit, belongs to Bob. So this is the one that Bob took with him. These are the two qubits that are a part of the entangled Bell state. So once more, ket psi is Alice's qubit that she needs to send to Bob, and ket beta 00 is the Bell state, right? This Bell state here that they created together. And once more, pink is going to denote Alice's qubits, and green is going to denote Bob's single qubit. So the initial state of the quantum computer, right, which is this right here, right? So at this moment in time, our initial state is going to be ket psi tensor the Bell state. And so if you want, you can pause here, but I'm just, expanding and distributing to get it in this form here. And so now Alice is going to send her two qubits through a controlled NOT gate, which is going to be controlled on qubit 0. So that's exactly what this CNOT is here that we're doing now. So we're passing these two qubits through this CNOT that's controlled on wire 0. Target is wire 1. So this is just breaking down the math here. So when we apply the CNOT, since qubit or wire 0 is the control, since here wire 0 is 0, so the control is 0, so we're not going to do anything. Here wire 0 is 1, so we're going to flip Alice's qubit here, these two qubits there. So, this is a single qubit, right, in superposition. So that's what we do here. That's what these arrows represent. And so that leaves us with this state. So on this side, we see that, we just carried this down. Since the control was 0, we didn't do anything. Since the control was 1 here, we flipped this 0 to a 1, and we flipped this 1 to a 0. And so now Alice is going to send her first qubit through a Hadamard gate. And so that's just this right here, right? We're sending wire 0 through a Hadamard. So that's exactly what I've written out here. So wire 0, right, that's these two. We're going to apply Hadamard to put them in superposition. That's what's going on there. And then I'm just going to distribute alpha and beta to these two terms here, which is just what this step is. After that, I'm going to distribute Alice's first qubit, right? So I'm going to be distributing these terms here. And so that's what we get here. And then as a last step, I'm now going to factor out Alice's two qubits. And so that's going to leave us with these four terms here. So out front, we'll have Alice's two qubits, and then the third qubit will be Bob's qubit, which is in superposition. So we now see that if Alice measures her two qubits, and say she reads 0, 0, right? Then she knows that Bob's qubit has to be in the state alpha ket 0 plus beta ket 1. That's this case right here. Because if we measure 0, 0, right, we know that Bob has this qubit. If Alice measures 0, 1, we know Bob has this qubit, or this, state. If Alice measures 1, 0, Bob has this state, and so on and so forth. So that's just in tabular form. That's all this table says here. And so the classical information that Alice sends Bob is just what she reads when she measures her 2 qubits, right? So just the 2 bits that she measures. And then according to what Alice sends Bob, Bob can just apply the appropriate gates to his qubit, right? Whatever he has here, to work back to the correct value of ket psi. So if Bob gets 0, 0, he does nothing, right? Because this is equivalent to ket psi, the original state that Alice was trying to send him. If Alice sends Bob a 0, 1, right? That's this one right here. Then we see that we need to just apply an X gate, right? Because we just need to flip these two computational basis states here. If Bob gets 1, 0, then Bob just needs to apply a Z gate, right, to flip this sign here. And then if Bob gets 1, 1, then he needs to apply an X gate to switch the computational basis states, and then also a Z gate to flip the sign. And so these will all get him back to the original ket psi. So that's all this is saying here. So if M1 is Alice's top wire that she measures, and then M2 is the measurement of the second wire, right? Qubit or wire 0, wire 1, wire 2, right? Indexing by 0. But here, M1 and M2 represent Alice's 2 qubits respectively. So this is just, this equation here, this formula is just, what we did here, but just as a function of M1 and M2. And then that is exactly what these gates up here are representing, right? We see that M1 and M2 feed into this, and then these are the gates that Bob then applies to get ket psi. And so now Bob can always recover ket psi from just 2 bits of classical information sent from Alice. And so you may be wondering, right, doesn't this allow us to send information faster than the speed of light? The answer is no, right? We avoid that paradox because Alice has to send her 2 bits, right, M1 and M2, to Bob classically. And so that is what disallows quantum teleportation to send information faster than the speed of light. So I hope this was a helpful explanation of how quantum teleportation works, and thank you.